Right now, NASA isn't just building rockets. They're racing to pick who might repopulate humanity on a distant alien world. With rising climate chaos, a ticking threat from asteroid impacts, and Earth's resources pushed to breaking, the agency's Artemis program marks our first step to survive beyond this fragile planet. The official plan sounds simple: moon base, then Mars. But buried in the mission timelines and base blueprints are the makings of a global backup plan, one where human DNA, frozen seeds, and AI systems could outlive Earth itself. The survival of our entire species could depend on how fast we move, and what NASA doesn't say out loud. So why is the moon now seen as humanity's lifeboat, and who will be chosen to lead the exodus? No planet has ever offered guarantees. In the fossil record, survival is measured in extinctions. Earth's surface, once a stable cradle, now tilts toward uncertainty. The average global temperature has climbed more than 1.2 degrees Celsius since 1880, with the last decade breaking heat records almost every year. Ice sheets thin, coastlines retreat, and wildfires redraw the map of entire continents. Each new report from the Intergovernmental Panel on Climate Change reads less like a warning and more like a weather forecast for a planet in flux. Population keeps rising, pressing against the limits of water, food, and arable land. By 2050, 10 billion people may crowd the continents, each demanding energy, shelter, and security. Resource conflicts, once distant threats, now shape policy at the highest levels. In some regions, groundwater disappears faster than rain can replace it. Crops fail, and migration follows. The world's safety net frays with every new crisis. Yet the real danger may not announce itself with warning. 66 million years ago, a single asteroid ended the reign of the dinosaurs. NASA's own calculations put the odds of a civilization-ending impact at about 1 in 100,000 per century, low but never zero. In 2013, a meteor exploded over Chelyabinsk, Russia, with the force of 400,000 tons of TNT. That rock was only 20 meters wide, missed being catastrophic by chance, and arrived without warning. The debate over how much to spend on planetary defense, or on building a backup home, drags on in Congress and scientific panels. Some argue the billions for Artemis and Mars should fix problems here. Others, like NASA's Bill Nelson, insist that leaving Earth is not a luxury, but a necessity. The numbers, the trends, the odds, they all point in the same direction. Staying means gambling on stability that Earth may no longer offer. For the first time, humanity's survival is a problem that begins with the limits of our own world. Artemis begins with a blueprint, not a flag. In 2022, Artemis 1 circled the moon without a crew, its systems quietly logging the data that would shape every mission to come. Artemis 2, now set for 2026, will carry 4 astronauts: Reed Wiseman, Victor Glover, Christina Koch, and Jeremy Hansen, farther from Earth than anyone before. Their brief journey will test deep space life support, navigation, and the limits of human endurance in the void. The real test comes on the lunar surface. Artemis 3 targets the moon's south pole, where sunlight and shadow carve a landscape rich with buried ice. NASA's plan: assemble the first modules of Base Camp, a pressurized habitat for 4, a mobile rover for weeks-long expeditions, and a utility vehicle built for the harshest terrain. The Foundation surface habitat, delivered by cargo lander, will shield against radiation and micrometeorites. The habitable mobility platform, part rover, part home, will let astronauts travel up to 45 days from base, carrying everything needed to live and return. Survival depends on using what's there. Water ice will be mined, melted, and split into oxygen and hydrogen, air, water, and rocket fuel. Solar arrays will stretch along sunlit ridges, while compact fission reactors are understudy for the 2-week lunar night. Dust, sharper than glass, threatens every seal and circuit, forcing new materials and constant vigilance. Orbiting above, The Gateway Station will serve as a transfer point and safe haven. Crews will move from Orion capsules to SpaceX's Starship lander before descending. Gateway acts as logistics hub, communications relay, and backup shelter. Each mission brings new hardware, new lessons, and the slow construction of a lasting outpost. International partners and private companies are essential. The European, Japanese, and Canadian space agencies contribute modules and robotics. SpaceX and Blue Origin expand the lunar foothold. As NASA Administrator Bill Nelson said, "The success of these early missions relies on our commercial and international partnerships." The moon is the test bed. Every recycled drop, every gram of oxygen, every circuit that survives the dust. These are the first answers to survival beyond Earth. Mars is a proving ground, not a promise. Perseverance, NASA's most advanced rover, has spent years searching for ancient water, caching core samples, and testing survival tools on a world where the air is almost pure carbon dioxide and radiation seeps through every grain of dust. In 2021, a gold-plated box the size of a car battery, MOXIE, began pulling Martian air through its chambers, splitting carbon dioxide into oxygen. 10 grams per hour, enough to keep an astronaut alive for a few minutes or fuel a small rocket. Michael Hecht, the MIT scientist behind MOXIE, called it a breath of fresh air on another planet. But Mars does not forgive mistakes. Solar storms can double surface radiation in hours. Temperatures swing from summer afternoons to Antarctic nights in a single rotation. Every kilogram of water, every liter of oxygen must be made or found on site. The Mars Sample Return Project, once expected to bring pieces of the red planet home by the early 2030s, now faces a budget ballooning past $11 billion and a timeline that stretches into uncertainty. Each setback is a reminder. Engineering on Mars is a negotiation with risk, and no solution comes without compromise. 5,500 worlds, each one a number, a dip in a star's light, a possibility. The Kepler telescope began the count, catching the faint shadows of planets as they crossed in front of distant suns. TESS continued the search, scanning wide fields for the rhythm of new orbits. Now, the James Webb Space Telescope turns its mirrors outward, not just to find planets, but to read their atmospheres. Transmission spectroscopy, light filtering through alien skies, reveals the fingerprints of water vapor, methane, carbon dioxide. Every molecule is a clue. TRAPPIST-1e, 40 light-years away, circles a dim, ancient star. It is almost Earth's twin in size and mass, orbiting where liquid water could exist. Its year lasts just over 6 days. Webb's data rule out a thick shroud of hydrogen, hinting at a denser, potentially life-friendly air. Yet the planet's true nature remains hidden. No confirmed atmosphere, no surface mapped. The search for a second home is not a fantasy. It is a catalog, growing by hundreds each year. Somewhere in the darkness, a world waits for its first visitor. Life's memory travels cold. At minus 196 degrees Celsius, liquid nitrogen suspends seeds, embryos, and strands of DNA in a state where decades pass without change. In underground vaults on Earth, these collections already hold the genetic blueprints of thousands of species. But on the Moon or Mars, refilling a tank is not an option. Engineers study vaults buried beneath lunar regolith, where night never ends and temperatures stay below minus 150. Digital genomes, DNA encoded with entire libraries, promise to store millions of species in a few grams, shielded from cosmic rays by meters of rock. Autonomous biofoundries, guided by artificial intelligence, could one day read these codes and rebuild life molecule by molecule. The hope is not just to save what we are, but to give future worlds the tools to begin again. No single engine carries us to the next star. For robotic scouts, the numbers are precise. A gram-scale probe, driven by a 100-gigawatt laser array, could reach 20% the speed of light, nearly 60,000 kilometers per second. Breakthrough Starshot, and NASA's Starlight project run calculations, test atom-thin sails, and measure the photon pressure that might one day launch our first interstellar emissaries. But human passage is another order of ambition. Light sails for people would demand power and precision beyond anything yet built, energy consumption that dwarfs today's entire global grid. Scientists turn instead to biology. In European labs, researchers have coaxed mice into torpor for a day, dropping their body temperature, slowing their hearts. In hospitals, doctors chill patients for hours to buy time after cardiac arrest. Yet no human has ever slept through a journey of years. The dream persists, a ship where generations are born, live, and die between the stars. Or a capsule where time folds inward and waking comes on another world. Survival, in the end, may be measured not just in speed, but in patience, adaptation, and the willingness to become something new. Since 2009, NASA and its partners have confirmed over 5,500 exoplanets, using telescopes like Kepler, TESS, and now the James Webb Space Telescope. The Artemis program is preparing the first sustained moon base, with missions underway and water ice extraction plans in place by the late 2020s. On Mars, technologies like MOXIE have proven it's possible to generate oxygen from the Martian atmosphere, while genetic preservation projects are storing DNA and seeds at cryogenic temperatures for future use. Yet, no current mission has found a truly habitable planet within reach, and many technical and ethical questions remain, especially about long-term survival off Earth. NASA's documents and mission statements make clear: the path to a second home is built on evidence, not assumption. As of now, Earth is the only world known to support life. But every new mission, from Artemis to the James Webb Space Telescope, brings humanity one step closer to ensuring our survival among the stars.